Okay, so in our previous video, we talked about the idea of a mathematical relation. So a mathematical relation essentially being a set of ordered pairs, meaning anything we can draw on the Cartesian plane. It might be one ordered pair, it might be 1 point, that would be a relation. It might be 5 points, it might be 15 points, or it might be infinitely many points that all form a straight line, or a parabola, or a hyperbola, or a square root function. Okay, so anything we can draw on the Cartesian plane is a relation. Today we want to talk about functions. So some relations are functions. Okay, so essentially functions form a subset of relations. Okay, so some of our relations are functions. All functions are relations. Okay, so that is, all functions are things that you could draw on the Cartesian plane. Okay, but there are certain restrictions to that. Okay, so not all relations are functions. It's not just any old set of ordered pairs. Okay, so there's a specific condition, and we've got that written here. A relation is a function if no two ordered pairs, so remembering that ordered pairs are coordinates. So if no two set of coordinates in the function have the same first element, so that is x coordinate. So if you've got a function, again, it's a set of ordered pairs, but it's a set of ordered pairs where no two ordered pairs have the same x coordinate. Okay, so let's just think about what that would mean over here before we talk about what it says further down the page. So let's say we've got some sort of function that goes through this point here, okay, whatever the coordinates of that point are, okay. So what that means is, if this is to be a function, there cannot be any other point in the function with the same x coordinate as that point. So if, for example, there was to be another point up here, so let's say the coordinates of this point is -2, 2. And let's say there's another point up here that's at -2, 5. Okay. These 2 points form a relation. Okay, it's a set of points on it's a set of ordered pairs, but they are not a function. Okay, because there are 2 points in this particular relation that have the same x coordinate. Okay, so when 2 points have the same x coordinate, it's because they're sitting vertically above each other. Okay, if I draw another point over here with the same y coordinate, for example, at 3, 2, okay, they don't have the same x coordinate, so that's fine. That's all right. Those 2 points would form a function. The issue is going to arise 2 points with the same x coordinate, so the issue is going to arise if they're sitting vertically above each other. So that means, for example, let's think about something. We'll talk more about some specific examples. So let's think about a circle, for example. A circle is not a function because there are at least 2 points on the graph that have the same x coordinate. That would be a problem. Okay, that makes that not a function. Whereas something like a parabola, that is a function because there aren't any points with the same x coordinate. Okay, there's points with the same y values, but that's okay. That's not an issue. But there are no points with the same x coordinate. When x equals 5, say for example, I don't know, when x equals 5, y will equal one particular number. Okay, it can't equal more than one number, so there aren't 2 points with that x coordinate of 5. Alright, so which of the following are functions? So the first 2 examples, we've got simply a simple set of points. Okay, so they're all relations, they can all be drawn on the Cartesian plane, but which of them are functions? Okay, so we're looking for the fact the relation needs to have no 2 points with the same x coordinate. Okay, so this relation has 3 points, and each of those 3 points has 3 different x coordinates, 1, 2, and 3. So this one's a function. No problem there. In the second relation, we have 3 points also, but these first 2 points have the same x coordinate, and so therefore this is not a function. It's still a relation, they're both relations, but this relation is a function, the first one, and the second relation is not a function. The third one is a parabola. We just talked about the parabola down here. So y equals x squared, this shape here, There are no 2 points on this graph that have the same x-coordinate. There's nowhere where we've got 2 points vertically above each other, okay? And so therefore, the parabola y equals x squared, or any parabola actually, is a function. Okay, so in terms of which of the relations are functions, that one and that one, those two are functions. So we've sort of lent towards this already. So a simple graphical test can determine if a relation is a function. So for a relation to be a function, any vertical line drawn to pass through the graph should only cut through the graph at one point. And that's about us checking whether there is anywhere where more than one point has the same x-coordinate. So for example, going back over here, I drew vertical lines here to help me think about it. So what you're sort of imagining is that you take a vertical line and imagine kind of sweeping it along the graph, the whole way along the graph, both directions. Everywhere along that graph, that vertical line should only hit the graph at one point. If there's anywhere on the graph, it doesn't need to be all points on the graph. If there's any point on the graph, any x value, where there are two y values, so there are 2 points with the same x coordinate, then it's not a function. Okay, so the circle, for example, it would be fine if I drew my vertical line here. It only hits the graph once there, but the fact that there are other places where we hit the graph twice means that this is not a function. Okay, so vertical line test. So imagine taking a vertical line and sort of sweeping it. Imagine sort of like a barcode scanner, sort of sweeping it across the graph and thinking about, okay, is that going to ever hit, will there be anywhere where that hits the graph more than once? Okay, so let's have a think about these functions then. So again, sort of imagining taking my vertical line, let's see if I can sort of do this, and grabbing it and then just sweeping it along the graph. Is there anywhere where that line would hit the graph twice? Okay, and there isn't going to be in this instance. So this one will be a function. All straight lines will be functions. Okay. Let's have a think about this next one. Let me grab my same straight line here. So if we take the straight line and we sweep it across the circle, we've actually already talked about the circle as an example of something that is not a function. This is not a function, for example, because we hit the graph twice. Here, for example, there's many other places where we hit the graph twice. It only has to happen once, so this one is not a function. The parabola, we've talked about the parabola shape already. So again, let's imagine we take a vertical line. I'm just going to grab that and then sweeping it across the parabola, thinking about, is that line only ever going to hit the parabola at one point at a time? Yes. Okay, so therefore this one is a function. And then the square root graph. So again, grabbing my line and sweeping it across my function. It doesn't matter that back here it doesn't hit the graph anywhere. The issue is it can't hit the graph more than once. Okay, so here we hit the graph once at that endpoint, and then as we continue to sweep along here, it'll only ever intersect with that graph at one point. So the square root, well, we call it a square root. I've been referring to it as a square root function for very good reason, because all square root graphs are indeed functions. Okay, so just the circle so far. In fact, the circle's the only graph example of a graph shape that we've met that is not a function. Okay. All right, so let's now talk about function notation. And we have met this sort of intuitively already. If you were in my class in Year 10, I cover this fairly explicitly in Year 10. And we've talked about function notation because it's a really handy way to use your CAS. We've also actually used function notation when we're doing polynomials, p of 2, p of 3. So we've sort of already done this intuitively, but let's just take a step back and be clear about what's happening here with this notation. So the definition of a function says that for each x value, which is a value in the domain, so for each x value in the domain, there is a unique element y in the range. Okay. If we had an x value which gave us more than one y value, by definition that's not a function. Okay, because if you've got a graph where this particular x value, whatever it is, when x equals this, y could either equal this or this, by definition you've got something that's not a function. Okay, so when we have a function, every x value produces one unique y value. Sorry, yeah, not necessarily a unique y value, but it produces only one y value, okay? If we think about a function as input and output, okay, our x values being our input. In science, you might talk about things like dependent and independent variables. So the x values being the independent variables, that's the data we put in. We do something to it according to the equation or the rule, and we produce output. Dependent variables if you're talking about your science experiments, okay? So thinking about a function as having input and output, the x values being the input, we do something to them, we double them and add 5, we square them and subtract 7, whatever it might be. We take the square root of them, multiply them by 2 and then add 5, okay? Whatever we do, we take the x values and we turn them, according to the rule, we turn them into output values, which we call y, okay? So thinking about it in terms of input and output. So we start with our x values, we put them into our function, whatever the function is, double and add 5, subtract 3 times the input from 7, whatever, okay? And that produces an output value, okay? Now the output value that comes out is a unique combination of the input value, x, and the rule, f, okay? And so we don't need a new letter, y. Okay, we don't need to call it something else. We can simply call it f of x. That's how we read this, okay? F of x, a function of x, a result of applying f to the input value x, okay? So since the value, that next sentence basically says what I've just said. Since the y value obtained is a function of the x value that we're substituting into the rule, we use the notation f of x in place of y. And so we can sometimes see that y equals f of x, but really we don't actually need there to be y in the problem at all. All right, so let's think about this simple function. So this particular function is take the input, multiply it by 3, and then add 4. Okay, so that means if our input is x, we apply the function f to it, which means we get f of x. Applying function f to x means taking x, multiplying it by 3 and adding 4. So f of x is 3 times x plus 4. If our input is 2, we apply function f to it, f of 2, we do function f to the number 2. That means we take the number 2, we multiply it by 3 and we add 4 to it. That gives us 10. Okay. If our input is 5a, we take that, put it into the function, which says multiply that input by 3 and then add 4 to it. So we're applying the function to the input 5a. We're doing f of 5a. We're doing 3 times 5a plus 4, which we can expand and simplify. Similarly, the input could be a more complicated algebraic expression. We take it, we substitute it into the rule, which says multiply that input by 3 and then add 4, and we produce our output. So applying the function to the input, 2x minus 2x, x squared minus 2x, sorry, means doing 3 times x minus 2x, x squared minus 2x plus 4, and obviously we can expand that out and collect any like terms and tidy that up. So we conventionally use the letter f as the name of a function. That seems pretty obvious, but actually we could use any letter. And it's common to see. We used p of x a lot when we talked about polynomial functions. We can use any letter, and they can be lowercase or uppercase. So let's complete the following tables then. So if we've got a function g, now that g is the rule, the sum of the square of the input and 5 times the input. So if my input value is x, then applying this rule g to x, g of x, means taking that input, which is x, squaring it, and adding that together with 5 times that input. So x squared plus 5x is a result of applying function g to the input value x. If my input value is 2, okay, I'm doing this rule to the number 2. So 2 squared plus 5 times 2. Okay, so thinking about, I might change my colours here. So 2 squared plus 5 times 2. Okay, so that's 4 plus 10, which is 14. Sorry. All right, if my input value is -3, putting -3 into the rule, into the function, doing that function, summing the square of the input and 5 times the input to the number -3. Okay, so this time we're going to have -3 squared plus 5 times -3. So that's 9 minus 15, so -4. Again, x plus 1 is my input. Okay, we put that into the rule for g. We do g to that piece of input, which means we square it and then we add it to 5 times that thing. Okay, so again, we're going to have something squared plus 5 times something. And in this case, that something is x plus 1. And then obviously we can expand that out and tidy it up. X plus 1 all squared is x squared plus 2x plus 1. Expanding the other bracket, 5 times x plus 1 is 5x plus 5. And so we've got x squared plus 7x plus 6. Alright, if we have function h. So h is the square root of 10 minus the input. So if the input is x, okay, we've got h of x. We apply this rule, h, square root of 10 minus the input, to x, which means we get square root of 10 minus x. If my input is 1, we get square root of 10 minus 1, which is square root of 9, which is 3. Please note that the square root of 9 is not plus or minus 3. Okay, can we be clear about that difference? If x squared is equal to 3, then x is if x squared is equal to 9, then x could be the positive or negative square root of 9. It would be possible for x to either be positive 3 or negative 3, and that relationship would still be true. If, however, x equals the square root of 9, okay, if we meant negative square root of 9, we would have written a negative out the front here. Okay, you don't just add the plus or minus in front of a number. Root 9 is a number. We don't just add plus or minus. If I told you x equals 5, you don't go, oh, that means x equals plus or minus 5. Okay, if x squared equaled 5, x equals positive or negative square root of 5. If you take the square root, you have to consider the positive or negative option, okay? But if the square root has already been taken, okay, this function is the positive square root of 10 minus x, okay? If it meant the negative square root of 10 minus x, it would say that there'd need to be a negative there out the front. Okay, so root 9 is just 3. It's not plus or minus 3. All right, so if my input is -5, so substituting that into my rule, we're now doing the square root of 10 minus that input, which is -5. So it's square root of 10 plus 5, which is square root of 15. So it's simplified, all done. If my input is 3a, doing h to 3a means taking the square root of 10 minus 3a. If my input is x plus 4, doing h to x plus 4 means taking the square root of 10 minus, now be careful here, because you need to subtract all of x plus 4. It doesn't say the same thing if you don't have the brackets. So it's the square root of 10 minus x minus 4, so that is the square root of 6 minus x. Okay, let's have a look at these functions here then. So we've got two functions here, a quadratic function and a linear function. So to be clear, we talked at the beginning about the definition of what a function is. We cannot use function notation, f of x, g of x, for something that isn't a function. Okay, and that's because there's not one unique value that's associated with x if it's not a function. So we can't call it applying the function to x because actually we can potentially get two different values when we do that. Okay, so let's have a think about understanding the function notation. So f of 0, okay, so that means where there's an x, 0 becomes the input to function f. Where there's an x in function f, we replace it with a 0. So this is 0 squared plus 5 times 0 plus 6. So it's just going to be 6. We would do f of 0 when we want to find the y-intercept of a function. It's letting x equal 0. As opposed to part B, which asks us for the set of x values where f of x is equal to 0. Okay, now this is f of x. Okay, that whole thing, x squared plus 5x, is f of x. And so therefore, what we're being asked to solve here is x squared plus 5x plus 6 equals 0. The set notation around it doesn't change anything. It's asking us to find the set of x values for this equation. So it just means that at the end, technically, if I've been asked for a set of x values, I need to give my answer as a set of x values. Okay, so we want to solve the equation. So this factorizes x plus 2x plus 3. And so therefore x equals minus 2 or, sorry, minus 3. So technically we were asked for a set, so let's give a set. X is an element of the set which contains the numbers -2 and -3. So remember the curly brackets means we can list out the set, -2 and -3. If I wrote round brackets here, that says something completely different. Okay, it said, and actually I should really have written them in numerical order, so let me write it as -3, -2. If I used round brackets, that says something completely different. Okay, that says the interval from -3 up to -2. That's including all of the numbers between -3 and -2. And technically with the round brackets, not actually including -3 and -2 at all. If there were square brackets, okay, now we at least include -3 and -2 in the solution set, but we're also including all of the numbers in between -3 and -2, which are not solutions to this equation. Okay, so just taking care with the differences in those notations. Okay, part C, we want to find again a set of x values, so at the end we'll make sure we give our answer as a set, and we want to find the set of x values where g of x is equal to 0. Now g of x is equal to 3x plus 14, and so therefore we want to know when 3x plus 14 is equal to 0. That is when 3x is equal to -14, and so x equals -14 on 3. And so therefore x is an element of the set which contains just one number in this instance, -14 on 3. Part D, find the set of x values such that g of x is bigger than 5. Okay, so again, g of x is equal to 3x plus 14, and we want that to be bigger than 5. So subtracting 14, 3x is minus 9. Dividing by positive 3, so no need to reverse your inequality, x is bigger than -3. Okay, and so therefore, now this time that's an interval, that's a range of values, x is bigger than -3, so this time x is an element of the interval that starts from -3 but doesn't include -3 and goes up to infinity. And then part E, we want the set of x values such that f of x is equal to g of x. Okay, so f of x is x squared plus 5x plus 6. So x squared plus 5x plus 6, and we want that to be equal to g of x, which is 3x plus 14. So we're going to solve this equation. So let's collect like terms on the left-hand side. So subtracting 3x from both sides gives us x squared plus 2x, and subtracting 14 from both sides gives us -8. Factorising, it's a simple quadratic. Factors of -8 that add up to +2. So that is x plus 4 and x minus 2. So therefore x is -4 or 2 using our null factor law. We're asked for a set of x values, so let's give a set. It's just a list of 2 separate values, it's not a range of values, and so curly brackets, -4 or 2. Okay, sorry. So then we want to talk about more formal function notation, which we haven't talked about before now. So when we define a function technically is only fully defined if we give both the domain and the rule. Okay? If we omit the domain, then we make assumptions about what the domain is. Okay? But technically we should really give the domain. We'll talk more about those assumptions, what we assume if there's no domain given, in the next video. I referred yesterday to something called the implied domain, which is what would happen. But technically, full formal function notation, we would always give a rule and a domain. And we do that using this particular notation. There's a number of parts to this, and really only 2 of them are particularly important. Okay, so let's work our way through the parts. So I'm looking at this section in here. Okay. All right, so the first bit is just the name of the function. Your name might be Will, or Chris, or Joe, or Jack. Okay, this function is called f. And then we write a semicolon. Okay, so f, we've got a function called f, such that, semicolon in maths is read as such that, okay? So it's essentially a sort of, like it would be in English, it's sort of, you can follow it with a definition. Now, then this first bit is the first important part. This part is the first bit that's important. That's your domain. I'm going to jump ahead, I'll come back to the next bit. And this part's the next bit that's important because that's the rule. So they're the two key things that define a function, okay? Domain and rule. That is, what is the input and what do I then do to it? You need both of those things to be able to execute a function, okay? What values am I putting into the function, and what do I then do to those values when I put them into the function? So the key idea is that a function takes input and it does something mathematical to them and it turns them into output. Okay, so some people are tempted, and output we call the range. Okay, now sometimes people are tempted to think that this is going to be the range. Now this isn't the range because we haven't actually, in terms of reading this function definition from left to right, what this says is we have a function called f. The input for that function is going to be all of the numbers between -2 and 4, including -2 but not including 4. Those numbers are all going to get turned into new numbers. We don't know what they are yet, but they're going to get turned into some sort of output, okay? And that is going to happen according to this particular rule. Now the point is we actually don't know what the range is at this point, okay? And we don't need to know the range to define the function. This function definition is going to allow us to work out the range. So this R isn't the range, okay? This is not the range. This is actually something called the codomain, which is just a set of values that we know that the range will fit within, okay? And so remember we talked about last lesson, or in the number sets video, sorry, the 2 videos ago, that in terms of maths methods, our entire world of numbers is the real numbers. We don't deal in any non-real numbers. So when we're talking about real functions like these, we know that whatever the input is, whatever we're going to do to that input, the output will be real numbers. It'll be a subset of the real number set. And so the codomain is a set of values that contains the range, okay? And so for our intents and purposes, we're always going to write R. So for us, we're going to always be R. So we'll have our function name, semicolon, our domain, arrow. So we read that arrow as maps to. So our domain, or our input values, maps to or are turned into values that fit within the real number set. And that happens according to this particular rule. We take those values, we square them, and we subtract 3 times those values. Okay. So the next thing is that 2 functions can have the same rule, but if they have different domains, then they're different functions. Okay. So the key thing about a function is those 2 things are important together. Okay. Domain and rule define the function. So even if you've got 2 different functions, 2 functions using with the same rule as we have here with f and g, if they have a different domain, it's a different function, and so therefore it needs a different name. Okay, so in this instance we've still got the same rule, but we have a different domain, and so we're calling this function something else. This isn't the same as f. This is a different function g. It uses the same rule, but it uses different input, so it's therefore going to produce a different set of output. There'll be some overlap, but it won't be the same. Okay, so let's have a look at these. Example 5 here. So we want to look at the following relations, and if they're functions, then we're going to rewrite them using this formal function notation involving both the domain and the rule. Okay, so we've got a set of x values where y is equal to x squared. Okay, so that's a parabola. So that's, so that is y equals x squared. Okay, so that's a function. We've already talked about that, so we're going to be able to write this using function notation. Okay, maybe let's use letter A, otherwise we'll run out of letters here. So part A, we'll call our function A. We need to know the domain. So the domain of a parabola, we talked about this last lesson, is R. Always, the parabola exists for all real numbers. So we're going to have R. So all those real numbers are going to turn into new numbers, but they will also be real numbers. And that's going to happen according to the rule. Now my function's called a, so therefore my rule is a of x, applying function a to the input values x, and that is x squared. So there's my formal function definition, function notation for that particular relation. Okay, part B. Sorry, so this time we have a function set of coordinates, such that y is equal to 2x minus 1. So that's a linear function, but we only want that where x is from 0 to 4. Okay, so 2x minus 1, something like this, but we're only looking at that from 0 up to 4. Okay, so from x equals 0 to x equals 4. So something like that. So we've been given the domain here, and it's not R. We're not assuming the implied domain. We've got some sort of restriction happening here. So let's call this function b, semicolon. We then need the domain, which we've been given in the question. So we're just looking at input values from 0 to 4. They are turned into new numbers, which are part of the real number set, and that happens according to the rule b of x equals 2x minus 1. Okay, part C. So thinking about that, x squared plus y squared equals 4. So that's actually not a function because that's a circle with a radius of 2. And so not a function, so we don't use function notation. And that's because we need to sort of have y as the subject to use function notation. If we make y the subject here, well, it's because it doesn't adhere to the definition that we have more than one point with the same x coordinate. But we're going to get this plus minus square root, and actually we can sort of break the circle into two separate functions. The positive square root, which is the top half semicircle, that's a function, and the bottom half semicircle, which is also separately a function, but together the whole thing is not a function. So if we got to this point, we could define two separate functions. F of x is positive square root, g of x is negative square root, but the whole thing together is not a function. So no function notation. Okay, so part D, we've got y equals x squared minus 2x, that's a plus 15, sorry, that's a quadratic equation, and we're only looking at that where x is bigger than 0. Okay, so whatever that looks like, it's a parabola, but we're not looking at all of it. It's restricted in some way. Let's say that's the y-intercept, the y-axis there, which will be at 15. I haven't drawn a perfect graph, but we're not looking at the whole parabola, just from where x is bigger than 0. Oh, sorry, and it should be a hollow circle there for the bigger than, greater than 0. Okay, so our function notation, I'll get rid of that because I'm not sure that's an accurate depiction of that particular function. I think it probably has x-intercepts. So we'll call this function d, semicolon, we give the domain, and we use interval notation. If we don't use interval notation here, we would need to list a set, and we would need to write set of x values where x is bigger than 0. Okay, you can do that, but it's not very common. It's much more common to use the interval, which is from 0 to infinity. And then our rule, d of x is x squared minus 2x plus 15. All right, part E, y equals 1 on x plus 3. Okay, so that's a hyperbola. So hyperbola translated to the left by 3 looks something like that. Okay, so a hyperbola is a function. You imagine taking a vertical line and sweeping that across your graph. You're only ever going to hit the graph once. You won't hit the graph at all at the asymptote, but that's okay. It's about not hitting the graph more than once. Okay, and so yes, it is a function, so we can write it using function notation. I'm not going to use e. Because e has another meaning. We'll talk about that in the next topic. E has its own mathematical meaning, so I'm going to use g of x here. I'll save f for part F. So g of x, or g, the function's called g. Now, its domain. We haven't been given the domain, but a hyperbola doesn't exist for all real values. It has an implied domain that is not R. So we talked about this in the previous video. So the domain of this hyperbola will be R excluding negative 3. And that's because negative 3 would be the value that makes the denominator of that fraction 0. So R excluding negative 3 is the domain. Those numbers are turned into other numbers which are real numbers. and that happens according to the rule g of x equals 1 over x plus 3. Okay, and then our final example here. So if our function is y equals square root of x, okay, so no transformations, we're familiar with our square root graph, it looks like this. So we'll call the function f for part f. The domain of this function goes from 0 to infinity, x values, includes 0, obviously can't include infinity. Those values are turned into other real numbers, and that happens according to the rule that f of x is equal to square root of x. Right, the last thing to talk about is the fact that sometimes it's necessary to restrict the domain of a function. And again, I've mentioned this previously, it's important to note that two functions with the same rule but different restrictions are different functions. So here we have three different functions that all have the rule y equals x. The first one's domain is R, so we're looking at the whole line. The second one, the domain is from -2 to 2 inclusive, so we're looking at just a section of that line with included endpoints. And then the third one is just where x is bigger than or equal to 0. So again, we're just looking at an unlimited section. It goes on and on forever out this way, okay, but it has an endpoint that is marked with a solid circle. Okay, so last example here, let's sketch this particular graph of this particular function. Okay, so again, the two key important things here are the rule. So we're drawing the graph of y equals -1 on x, and the domain. We're drawing that only where x is between 0 and 5, not including 0 but including 5. Okay, so we're sketching y equals -1 on x. So it's a hyperbola that's being reflected in the x-axis. That's that negative. Okay, so again, don't launch into drawing this just yet. So reflecting the hyperbola in the x-axis means we get this here and this here. Getting a bit closer, veering towards my x-axis. Again, really taking care with the shape. It really is important to show that you understand about asymptotes. Okay, so that would be the graph of y equals -1 on x with no restriction at all. But we only want to draw this graph for this domain. So where x is bigger than 0 but less than or equal to 5. Okay, so therefore we don't want this bit up here at all. Okay, so x is bigger than 0 but less than or equal to 5, wherever 5 is. We're essentially only drawing it over that range there. So bigger than 0 is fine. There's an asymptote at 0. The graph doesn't exist at 0 anyway. So we're not going to draw it there. But we're going to stop when x equals 5. Okay. Now, you can't just stop a graph in the middle of nowhere for no good reason. If you stop it in the middle of nowhere, you need to be clear about whether that's an included or not included point. In this case, that's included because 5 is included in the domain, and you need to label that point with its coordinates. So when x is equal to 5, subbing it into our equation, y is equal to -1 over 5. And so the graph stops at the point 5 -1/5, but continues towards the asymptote. Don't need to label the asymptote with an equation in this instance because it is the y-axis, but if it wasn't the y-axis, we would make sure we label that with an equation. Alright, technically you should probably have another point because we haven't got an intercept. You could pick a point, for example, when x equals 1, y equals -1, so I might just also mark one other point for completeness so that the graph can be fully identified. Okay, so the last thing here is that this little box talks about using function notation with your CAS, okay, and we've talked about this already in the context of application problems, so I might leave you to have a read through this bit. But the key thing is there are two ways to define a function using your CAS. One is in the calculator screen to use menu 1 and actually define the function yourself. So if I define f of x, or you could use a different letter, let's use g of x maybe. If I define g of x as being x cubed minus 5x plus 1, okay, and then I can use that function. So g of 2 would mean substituting 2 into that function, solving g of x would equal to 0 would mean making that equation equal 0. That would be how I'd find x-intercepts. Sorry, I pressed Control Enter to get them as a decimal there, or Enter to get nice exact values. The other way you can define a function is when you draw a graph. Okay, so when I draw a graph, so let's say I draw the graph of x squared plus 2x. Okay. If I want to then use that function definition, I can. So automatically by drawing the graph, we've now defined f1 of x as this particular rule. So over in my calculator screen, if I type f1 of x, it should bring up that rule. Therefore, if I type f1 of 3, changing the input to 3 squared plus 2 times 3, it will work that out. If I solve f1 of 3 equal to 0 for x, it will solve that equation, which in terms of the graph, oh sorry, not f1 of 3, there's no x, sorry, f1 of x equals 0 for x. It's going to calculate the x-intercepts of that graph. If I were to complete the square for f1 of x, it would write my function, sorry, needs comma x, it would write my function in turning point form for me. So that allows me to find the turning point. So making use of function notation is really important with efficient use of your CAS. If you've got a function at the start of a question, then you're going to need to do lots of things with it. Define it yourself first, or draw the graph first so you've got the function defined and then you can use that. Okay. So again, there's some summary of that in that little box there. The work today is exercise 5C, and there's the list of questions.